picture here. L3 is the length. And it's got a spring attached of stiffness K. So there's the spring, stiffness K. And that is its linked distance L2. So the length L2 is from here to here, and the length L3 is the length of the beam, which is up to here. And you're all familiar with this system because you've done it before, and if you do this, it will vibrate at its own natural frequency. The difference this time is that we've got this big mass attached to it here. And this mass has got a motor within it, which will cause that to spin, and that will cause the whole bar to vibrate. So this mass is big M, and it's attached here, and it's big M. So there's two different masses involved. There's the big M, and there's the little m, which is the mass of the actual rigid bar. Now, the total moment of inertia is I0, and this is given by little m, which is the mass of the bar again, times L3, which is the length of the bar, squared, divided by 3. And that's the second moment of mass, or moment of inertia, for a rectangular, rigid bar about this axis here. So remember, when we do the equations for this, we're taking moments about this axis, because when this vibrates, this force in the spring will cause this to go up and down and vibrate about this axis. So we take all moments about here. So just to be sure again, we've got a mass here, this bar. We've got a big mass attached. This will spin and cause it to vibrate. Okay, so when you do the analysis for this, you've got all the information here, which is the big mass is 5 kilograms. You've got a little mass, which is the mass of the bar, which is 1.93 kilograms. And you've got the spring stiffness, which is 864 newtons per metre. Okay, for the experimental procedure is as follows. First of all, we want to know the natural frequency of the system that we're dealing with. So the way we do that is what we did in previous lectures. We just give it a kick, and on this screen over here, we can measure the actual natural frequency. So there will be some sort of oscillation. The next step, having got the natural frequency, is that we apply the forcing frequency, which means that we're going to basically spin this up. And we spin this up with this box here. So basically we twiddle this knob, and we twiddle it, and you can see that not much happening. And as you twiddle it up, at some point you can see this is starting to rock up and down. This is called harmonic excitation. And if we keep applying a signal to this, in other words, the frequency at which this is going round is the frequency of the forcing. If we keep applying this, then at some point we're going to approach the natural frequency, and you can see that we're going to get larger and larger amplitude vibrations. And if you look at this, it's rocking up and down quite aggressively, and this is approaching what we call resonance. If you undo it down a little bit, then you can see that you get some sort of more haphazard type response, and you could actually get what we call beating phenomenon, and we've also discussed that in the lectures. So Paul will explain that, but just to give you an overview, we're going to do 3 sets of experiments. The first one, we take the natural frequency of the system, and then we take the forcing frequency at resonance. The second thing, we're going to apply a mass here, which means that we change the system. So therefore we need to change the natural frequency, therefore we need to record the new natural frequency. So you do exactly the same experiment, and then you reapply the forcing. And of course the third experiment will be where we change the position of this mass. And remember, we're talking about moments and not forces. So it's not just the weight of this mass that we add, it's also the position, because it's the weight times the distance. So the distance is this distance here, which is L1, If we change that distance, we change the moment exerted, and so we're going to do that as well. So we're going to shift this over here somewhere, and again we're going to have to take the natural frequency and then the forcing frequency. Okay, so from now I'll hand you over to Paul.
So the system itself, as Jess explained, we push the beam down, allow the beam to vibrate. The oscillations will be recorded with this displacement transducer, and this displacement transducer is connected to a picoscope. And the picoscope is connected to the software. What we'll get initially, we'll get an oscillation on the top screen when we start capturing. When we've captured a number of cycles, we'll stop capturing, and then our screen, a new screen will appear at the bottom. This is the screen we're going to work on to find a natural frequency. So start system scanning. Click on the green icon at the base, start capturing, we get a horizontal line on the top screen. Force the beam down and release. The beam is oscillating and the oscillations appear on the top screen. We've got a sufficient number of cycles, stop capturing, and now our image appears on the bottom screen. We can adjust the zoom frequency from in here, this box. We have two cursors. Cursor 1, where we set on the initial peak. That time appears here. And we have our second cursor, which we want to set at a convenient number of cycles. And that will appear on the second box. The third box is the difference between those two cursors, their time value. So if you know the time value, and you know the number of cycles, you'll be able to find the natural frequency for the system. That's part 1. The next part will then be to force the beam. We switch on the motor, we start the motor oscillating, forcing the beam. So the beam is, the units are in revolutions per minute. And once we get to that point, we will start capturing again. Case of being patient. So it's quite difficult actually to find that point. In the case of being patient, I'll write that down. So now we're going to increase the mass on the motor. So we're now going to increase the mass onto the motor. We're going to increase it by 2 kilograms. So we're placing these individual weights on, and then we're going to lock to secure the weights in position. The beam is dropped, so we now need to bring the beam up into somewhere in the midpoint. We do that by bringing this handle, which then raises the beam to approximately the mid position. And once we've done that, we're then going to take the natural frequency once more. So the same process. Click on the green button to start capturing. Force the beam to oscillate. Allow for a number of cycles to appear and then to stop capturing. and their image appears at the bottom of the screen. Once more, bring the first cursor to the first peak, second cursor to a convenient number of cycles. Note those number of cycles, note the time between the two cursors, and find the natural frequency. And then, as before, we're going to set the beam oscillating by increasing the speed on the motor. So I'm getting there now.
So,
Yeah. Obviously, we don't want to go too excessive. So again, same process. Take our two cursors, find the time difference, make a note of the number of cycles, and find the frequency.
okay, what you're seeing here on this screen is you're seeing a beating phenomenon, and if you look at this, it's sort of got a little pause in it. So it's vibrating up and down, it stops a tiny little bit, and then it's vibrating again. So it's just in that beating regime. Okay, so what you can see here is two frequencies. You've got a frequency, or a period if you like, from here to there, that is from that point to that point, and within this you've got these other little superimposed vibration. So this is a phenomenon of beating, and you can also see there's a little bit of damping, so the whole thing is dying down over a period of time. And one of the things you've got to understand is, or try and report on, is why that damping, where it comes from, and why it would occur. Okay, so it's a good example of beating. You've got a period from here to there, or there to there. There should be the same period. And then you've also got another little frequency, another little period of these little waves on their own. If we actually increase the frequency from this, this should be close to resonance. If we increase it a bit, which is what I'm doing now, you can see that we're really getting large amplitude vibrations, and this is basically something to be avoided. And if we're not careful, it would actually damage the system. And if we increase this beyond resonance to a very high frequency, then you can see that the vibrations start to go down a little bit. And why do you think that is? Because that's something you need to look into the notes. So the question is, what's going on there? Why are we getting very small frequencies in the response? Very small amplitude of response. So we come down, we can come down slowly, there's a sort of time lag slightly in the response. As we come down, you can see this beating phenomenon is coming up again, and as we decrease it, we've got a larger amplitude of vibration, and we can sometimes sweep straight past resonance, but we may just hit it. So when you do these experiments, you can see now it's getting a larger amplitude vibration. And if I decrease it more, we're getting even very close to resonance now. And if I come down, I can avoid all of that. And it's just rocking away frequency which is vibrating is the frequency that you basically drive it at here. And that's always going to be the case. The issue though is what is the damaging frequency that you need to avoid, and that is basically large amplitude vibration or resonance is the theoretical one, but you never actually achieve resonance in a real system because you've got friction, but you can get close to it. So this is where this is going to vibrate a bit madly and it could damage the system, and this is something you need to avoid as a design criteria. Okay, so for this position, the whole mass is moved towards the axis here, which means that we've actually changed the inertia of the system. So the reason we've done that is we changed that distance L1. So remember, this is the total moment of inertia is now changed, and what this means is that the natural frequency will change. Remember that natural frequency is essentially KL squared, which is the stiffness K times the length here, L squared, divided by I, being the second moment of mass. So if you lower I, and by changing this distance, if you make that smaller, you change I and make that smaller. Therefore, if you make I smaller, the natural frequency goes up. And so essentially this is how this system will work. So you can see here we're getting quite close to a larger vibration. And you can see this is approaching a damaging situation, like where something is into resonance. There's a knock in the sides. So obviously it's something you want to avoid. So we go beyond that. Calm it down. And that's taken that away. Or we can come back again, and come through here, and if we sweep through quickly, then there's a delay because of the momentum in the system, and we can avoid it and come right back down. So this is a lower frequency driving force, but you get quite a large amplitude vibration nevertheless, until we go to very, very low here, and even then it's rocking around quite a bit. And we can keep reducing that until we take it completely out. And you can see the momentum there, so you're excited the system is still carrying on vibrating a little bit, until the damping in the system will cause that to die away.